Okay, so ladies and gentlemen, so welcome to our Math 4427 online lecture. Okay, so in this online lecture, I will continue our discussion on the property of the MLE, so which is something that we stopped at last time before the class was suspended. Okay, now so here just let me briefly recap what we have done in the last lecture. Okay, so here in last lecture, so we try to study the property, some important property about the MLE. Okay, so let's say the S is follow certain distribution with some unknown parameter. Okay, theta. Alright, and here let's assume that it is just a single parameter. And then given the random sample, okay, that you draw from the distribution, then you can use the maximum likelihood method to find your MLE, isn't it? And then last time, so we tried to study the property of this MLE. So by finding the, let's say, the mean square error distribution or stuff like that, right? Okay, so here remember, let's assume that it follow the let's assume that your PDF satisfies some regularity condition, and provided that so your MLE is obtained from the first order condition. Okay, then we can argue that first of all, the MLE is asymptotically unbiased. Okay, in the sense that if we take the expected value on this MLE, so it should equal to the true value, isn't it? And then the second property is it is consistent in the sense that it will getting close to the MLE getting close to the true value when n tends to infinity, in the sense that so the probability that your MLE is far away from the true value is getting close to 0. Okay, and the third one, which is also important, is so when n tends to infinity, this theta n hat will follow the normal distribution with the mean equal to the true value, and then the variance is 1 over I theta. Okay, so remember this one will be useful for you to get your mean square error of this estimator, and also we can also use that to construct your component interval. Okay, and of course finally we can also show that so this theta n hat has the lowest MLE. Has the lowest mean square error, not MLE. Okay, so that this is the best estimator that we are looking for. Okay, now and then then this is something that we have discussed before. Okay, and then of course in this property, so we assume that we only have one single parameter. Okay, but of course in some cases, so we may be working on the distribution with multiple parameter. For example, so it could be the Pareto distribution, so it will has 2 parameter, right? Or maybe gamma distribution, so it also has 2 parameter. Okay, or maybe not normal. Okay, so it has 2 parameter mu and sigma. Okay, now then again, okay, so given the sample data, of course you can obtain the corresponding MLE. Okay, and then just like the case for the single parameter, so this will be a random variable. Okay, and then here because it involves more than one variable, so then this one will be what we call the vector of random variable. Okay, then the next question here is, so when you encounter this random variable with multiple parameter and you want to construct a confidence interval about of this true value of the parameter, then of course you have to know the distribution of this thing, right? Okay, and of this, right? So here, okay, then we would like to see, okay, so let's say if you have multiple parameter, so then what will be the distribution of this guy there? Okay, so here actually we can try to show that. So let's say if you have a distribution with 2 parameter, okay, so let's say theta 1 and theta 2. Okay, and then we let the theta 1 hat and theta 2 hat be the corresponding MLE. Okay, so actually we can try to show that so when n is sufficiently large, so actually this theta hat will has what we call the multivariate normal distribution with the mean equal to the true value. Okay, and then the variance will be captured by this covariance matrix, so which is the inverse of this I theta. Okay, and here this I theta will be this 2 times 2 matrix, so which is given by this way. Okay, now and here in order to just have a little bit better picture about what this theorem is about. Okay, so here let me first try to briefly explain. So what is this multivariate normal distribution? And to see this, so we first we visit the normal distribution, okay, for the single random variable case. Okay, so remember, let's say, okay, we got the S which follow the normal distribution with the mean, mu, and the standard deviation sigma. So remember, one property is, so if you consider this as standard score, so it will follow the standard normal. Okay, then given this, so the S can be written as mu plus sigma set. Okay, and the set will follow the standard normal. Okay, so here then this is just another representation for the normal distribution. So that means S follow the normal distribution if and only if it can be expressed into the forms of mu plus sigma set, and the set is standard normal. So given this, then you can try to define the multivariate normal distribution as follows. Okay, so the idea is we let the S be a vector consists of n random variable s1, s2, sn. Okay, then we say it follow the multivariate normal, so if and only if it can be written as the form which is similar to this, so which is equal to mu plus a and then set. Okay, so the only difference here is because it is an n-dimensional vector, so that the mu here will also be what? A n-dimensional vector as well. Okay, and then here the set, okay, will also be what? Upgrade to n-dimensional vector as well. Okay, and then here, okay, so this each of this z I, okay, is the standard normal, okay, and is independent. Okay, and then here the A, okay, will be what? Just n times a matrix. Okay, so here, okay, then this is the definition of the multivariate normal distribution. And then so you can see, so this is just a extension from the normal distribution that you see in the single variable case. Okay, and then here just a little bit more information about this multivariate normal distribution. Okay, now first of all, just like the normal distribution, so it will have some parameter. Okay, now remember for normal distribution, so you have 2 parameter. So one is the mean, another one is the variance. Okay, and then similarly, so if you have a multivariate normal distribution, so actually this will contain, it will also has 2 parameter. Okay, so one again will be the mean. Okay, and here, okay, so that will, so in the case if you have n random variable, so the mean will be a n-dimensional vector. Okay, and then here each of these will be the expected value of the individual SI. Okay, and then besides that, so it also has it will also has another parameter which capture the variance. Okay, but just if you have a multiple random variable, so actually to describe the variance, so we will try to make use of the covariance matrix. Okay, so formally this covariance matrix is defined as something like this. Okay, maybe I erase this. Okay, so the covariance will be something like the collection of all this sigma will be a kind of n times n matrix. Okay, and such that this sigma ij, okay, each entry here, okay, will be the covariance between SI and SJ. Okay, so and then here, okay, so then this is how do we capture the variance of this n random variable. Okay, and here, okay, so if you look at the diagonal entry, okay, so you have sigma 1 1, sigma 1 2, sigma n, right? So remember, sigma 1 1 by definition is equal to covariance of S1 S1. Okay, and then according to the definition of covariance, so that will be equal to the variance of S1. Okay, so that here that the diagonal entry will be the variance of S1, variance of S2, variance of SI. Okay, and then for other, okay, so then there will be a kind of covariance. Okay, so that means so this covariance matrix actually try to capture the variance of each of these individual random variable, and what's more, it also captured the covariance between a pair of random variable, because this will also affect the fluctuation of the random variable, right? So then this is a covariance matrix, so which is another parameter, okay, in your multivariate normal that describe the variance. Now and then here, so according to this result, so we see this pair of the MLE, so we'll follow the multivariate normal distribution. Okay, now and then here, so if we try to compare with the case for the single parameter, so I would say this result is in fact it's just a direct extension from single parameter case. Okay, so to see this, so let us try to write down. So let us try to compare these two results. Okay, now so for single parameter case, so remember, okay, so this theta hat, okay, will follow the normal distribution with the mean equal to the true value. Okay, and then the variance is 1 over I theta, so which can be written as I theta to the power of -1. Okay, and then now if you have two parameter, okay, so actually it follows what? The multivariate normal. So let me just write that as n2. So 2 means, so n stands for the normal, 2 stands for the number of random variable, okay? And then the mean is what? Is theta 1 and theta 2, so which is parallel to this. Okay, and then here the variance will be so I theta, the inverse of the I theta. Okay, it's just essentially the same. Okay, now and then here for the single parameter case, so remember I theta is so I theta is equal to the minus n and then expected value of the second derivative of the log of fs right, isn't it? So which is something like that. Okay, and here actually for the two parameter case, so actually you can see this I theta also contain this the term which is something like that, but just like here, because you got a we got a function of two parameter, right? Okay, so when we talk about the second derivative, so they are all together 4 combination. Okay, so that's why it become a 2 times 2 matrix instead. Okay, but here, okay, then by noticing this, so you can see actually these two theorems are very similar. Okay, but just for multi-variable parameter cases, okay, so we have a little bit slightly more complicated structure. Okay, and then of course if we really want to prove this, okay, so I would say the proof is parallel to the case for the single parameter. Okay, so so the idea is, so again, in order to just a little bit outline here. Okay, of course I'm not going to go through the proof because it's extremely tedious. Okay, now so again, just like the single parameter case, the first step that you should do is, so you should first obtain the formula for the theta 1 hat and theta 2 hat. Okay, in order to figure out also which distribution does it follow, right? And then to get this distribution, so again, we will assume that so these two MLE follow the first order condition. Now, and then remember, if you have two parameters, so the first order condition will consist of two equations, right? Isn't it? So you need to differentiate the log likelihood with respect to theta 1 and theta 2 one time and then set u to 0. Okay, now and then again, in order to get this theta 1 and theta, this formula for the MLE from this first order condition, then what you do is you try to apply the Taylor expansion. Okay, and then you expand that and try to obtain the formula for this theta 1 hat, theta 2 hat. And then here, you can find the details in this appendix B. Okay, so of course, the idea is very simple, but just of course the calculation may be a little bit complicated. Okay, so I guess I'm not really go through the details. Okay, so you can try to look at this appendix. Okay, and try and look at the details. Okay, and then of course after you get this formula, then you can try to argue that it follow the multivariate normal using the central limit theorem as well as the strong law of large number. Okay, so again, so the scratch is presented in the appendix B. Okay, now but anyway, so forget about this technical proof at this moment. Okay, so let us just focus on our goal. Okay, now so here, okay, then we know, so when n tends to infinity, it follows the multivariate normal. Okay, then of course using this, then you can now try to use that to construct a confidence interval of your parameter in your distribution. Okay, so here just like what we did for the single parameter case. So our goal is, so given the sample data that you obtain, so is it possible for us to obtain the range of the true value of the parameter? Okay, so let's say if you have two parameters, theta 1 and theta 2, so our question is, so is it possible to find this 100p confidence interval for theta 1 and theta 2 respectively? That is, find the range of this so that this prediction is true with probability p. Okay, now and then in order to get this, so remember to get the confidence interval, okay, so the first thing that you have to do is you have to get the distribution of your estimator, so which is your MLE, right? Okay, now and here, given that, so your pair of these MLE follow the multivariate normal. Okay, then my question is, so is it possible for you to get the distribution of a single MLE? Okay, now and here, in order to do this, then we will try to make use of one property of the multivariate normal distribution. Okay, so what is that? So here, remember, let's say if you got a random variable s, so which follow the normal distribution with the mean, mu, and the variance sigma square. Now, so remember, if you consider AS plus B, so it will follow the normal distribution with mean A mu plus B, and then the variance A square sigma square. Okay, now and here actually we have the similar result for the multivariate normal. So let's suppose the vector S follow the multivariate normal with the mean equal to the mu vector and then the covariance matrix sigma. Okay, and then here let us consider the similar linear sum AS plus B. Okay, and here, okay, the A can be n times n matrix. Okay, and then B will be a m-dimensional vector. Okay, so that this guy will be a m-dimensional vector. Okay, so let's suppose, okay, we consider this sum. So A and B are just constant. So actually we can derive the similar result, okay, using the definition. So it will follow the multivariate normal, okay, with the mean equal to A mu plus B, and then the covariance matrix is A sigma A T. Okay, of course you can try to prove that using the definition. Okay, so you can take a look on the appendix A if you are interested. Okay. Of course, you can also look at our another tutorial video, okay, about the wet-out random variable. Okay, so you can get more detail about this. Okay, now so here let us just try to take it for granted, okay, and try to see so how do we use that, okay, to achieve our goal. Okay, now so here, okay, remember our theta 1 hat and theta 2 hat follow the multivariate normal, right? Then to get the distribution of a single MLE, so what you can do is you can consider this linear sum. Okay, remember that according to the property of the multivariate normal, so whenever what values of A and B, so it must follow the multivariate normal, right? Okay, with the mean equal to A mu plus B, and then the variance is A sigma A transpose. Okay, now so here, okay, our goal is we want to try to find the distribution of the theta 1 hat. So what I'm going to do is, so I will choose this A and B such that this sum will be equal to theta 1 hat. Okay, then let's say if this is successful, then I can use this result and find my distribution of my theta 1 hat. Okay, now so to do that, so what you can do is, so you can try to consider the A equal to 1 0, and then the B is just a zero vector. Okay, so in that case, so if you consider this, so this one is 1 0. Okay, and then B is a 0, so you can cancel it out. Then here, if you take the matrix product, then you will get the theta 1 hat, right? Okay, so here, then according to the property of this multivariate normal, then you can deduce that, so this theta 1 hat, okay, will follow this multivariate normal distribution. And because this is just a one dimension, right? So that means this is just a normal distribution, and the mean will be equal to A mu plus B, and the variance will be A sigma A transpose. Okay, then you just put in the A and B, okay, and do the computation. So you will find that the theta 1 hat will be equal to the will follow the normal distribution with the mean equal to theta 1, okay, and then the variance will be sigma 1 1, so which is the first diagonal entry of your covariance matrix. Okay, now and then also so then this is the case for the theta 1 hat. Of course, you can also do the same for the another parameter. So to get this, then you can choose the A equal to 0 1, okay, and then B will be equal to 0. Okay, so in that cases, if you have A theta 1 theta 2 plus B, so that will be equal to 0 1 theta 1 hat theta 2 hat, so that will be equal to theta 2 hat. Okay, so here, okay, then using the same property, then you can argue that the second MLE will follow the normal distribution with the mean equal to theta 2, and then the variance is sigma 2 2, which is the second diagonal entry of your covariance matrix. Okay, so here, okay, then this is how do we get the distribution of the single parameter. Okay, so after this, so let us try to take a look on some numerical example. Okay, so here in this example 29, so I try to reconsider the example 18. Okay, so the story is something like that. So let's say we have the claim amount in a single claim, so it has the normal distribution. With the unknown parameter mu and sigma. Okay, and then here we would like to estimate this mu and sigma. So we try to take out a random sample of size 20. Okay, so we list here. Okay, and then so using the maximum likelihood method, so we find that the maximum likelihood estimate of the mu and the sigma will be the mu equal to 6.1379, and here sigma square, Okay, so I made a typo here. So will be 1.9305. So which is the result that I call it from the example 18. Okay, so of course, if you want to know the derivation, so you can just revisit example 18. Now, and then what I'm going to do is, so I want to find the 98% confidence interval for each of these mu and sigma. So that means I would like to find out the range of the mu and the sigma such that this prediction correct is 98%. Okay. Now, then the question will be, so how do we get this? Okay. Now, so here, before I move on to the detail, so let us just have some outline here. Okay. Now, so first of all, let us consider the case if we want to find the 98% confidence interval of mu. Okay, so remember that in order to find this confidence interval, what we need will be the distribution of your estimator, which is your MLE in our cases. Okay, and then here remember, so in this situation, so we have two parameters involved in the distribution. So assuming that, okay, so your sample size is sufficiently large, okay, so which is may not be too realistic in this example, okay, but here let's assume the n is sufficiently large, then we know, so this MLE, this pair of the MLE, mu and sigma, will follow the multivariate normal distribution. Okay, so with the mean equal to mu and sigma, and then the covariance matrix will be this, which is equal to the inverse of this matrix I theta, isn't it? And then here, so given this distribution, so we know, so if we just focus on the single parameter mu, so it will has a normal distribution with mean mu, and then the variance will be sigma 1. Okay, and this is so this is the distribution of the mu hat. Okay, and then so here, in order to move on, so it seems like that we have to first obtain this sigma 1 first. Okay, and in order to get this, so it seems like that you have to find what is this I theta in order to take the inverse and get your covariance matrix. Okay, now so here just recall what is your covariance matrix. So your I theta. So your I theta will be equal to the matrix of this thing. Okay, so which is the expected value of the second derivative of your log of your distribution function. Okay, and then let me see, put enough space here. Okay. That's your I theta. Okay. Now and then here, in order to find this I theta, so you have to obtain these 4 expected value. Okay. Now so here, in order to compute this expected value, just remember the procedure that we use in our class. Okay, so first of all, you first try to obtain the formula for your log of fs. Okay, so here just recall, for log normal distribution, so the PDF will be given by this formula. Okay, then so after you take the log, okay, so then this distribution function can be separated into 4 terms, 1, 2, 3, 4, like that. Okay, just the property of the log function. Okay, now then the next step is, so given this, then we try to compute this 4 expected value. Now then the second step we try to do is, so here let's say if I want to calculate the first expected value, I mean this one. Okay, now then to compute this, so first of all we first forget about the expected value and first focus on this second derivative. So meaning that you try to first differentiate this log function with a log of this distribution function with respect to the mu. Now and then here you can see in the for the first term, so there's nothing to do with mu, so that it will become 0, right? Now and then for the fourth term, okay, then if you differentiate it one time, okay, so what you get will be something like -2 and then natural log s minus mu, okay, divided by 2 sigma square. Okay, it should be passed. Okay, then that is the first derivative. And then if you differentiate one more time, okay, then you will get -2 divided by 2 sigma square. Okay, so then this is something that what you see here. And then because this is just a totally constant, nothing to do with s, so that when you take the expected value, actually it doesn't change anything. So that once you cancel out the 2, then this is the first expected value. Okay, now and then how about the second one? Okay, now for the second one, so that will be the second derivative with respect to the mu and the sigma. Okay, and one time each. Now so to do that, so here first recall, if we differentiate this function one time with respect to mu, so then this is what you get, right? And then if you try to differentiate it with respect to sigma, okay, now and then so you will get -4 natural log s minus mu divided by 2 sigma to the power 3. Okay, and then here you can cancel out the 2. Okay, then this is basically what you get. Okay, and here just be careful that the small s should be the capital S, so we should say random variable. Now and then in order to move on, so you have to compute this so you have to compute the expected value of natural log s, okay, which is the only random variable in your expected value. Now to do that, remember, because s it has a log normal distribution, right? So by definition, then the natural log s will follow the natural log s will follow the normal distribution with the mean, mu, and the random sigma square. And then if you are asking for the expected value of natural log s, so that will be equal to mu, isn't it? Okay, so that's why here, okay, once you take the expected value, so this expected value of natural log s will become the mu here. Okay, and then for other, because it's just a constant, so it doesn't change. So here after the calculation, so you get the value equal to 0. Okay, now and then for the third one, so because this law of this fs is kind of twice differentiable and is continuously differentiable, so that here, okay, if we try to reverse the order of the differentiation, so actually it will give you the same answer. So meaning that if this expected value equal to 0, so this one will essentially give you the same answer. Okay, so here, so both of these will be equal to 0. Okay, now and then lastly about the expected value of this second derivative with respect to the sigma. So basically you just differentiate this log function twice with respect to sigma, but just be careful that so there will be 2 terms involving the sigma. Okay, so you try to differentiate each of these with respect to sigma 2 times. Okay, then this is basically what you get. Now and then in order to continue the game, so for the first term it is a constant, so you can just take that out. And then how about the second one, okay, which you have the natural log s minus mu all square as a random variable. Okay, and then to do that, so first of all we call that the mu is just equal to the expected value of the natural log s. Okay, so that this one will be equal to the expected value of natural log s minus the expected value of natural log s and then all square. Okay, and then by definition, so this one is just equal to what? The variance of natural log s. And then remember that, so log s follow the normal distribution, so the variance will be sigma square. Okay, so we are done. So you just put that in, and this is what you get. Okay, then once you get this four important expected value, then now you can put it back into your matrix I theta so that you can get your I theta will be equal to this matrix. Okay, so which is the very nice one. Okay, diagonal matrix. Now and here, in order to obtain your covariance matrix, so you have to get the inverse of that. Okay, so remember covariance matrix will be equal to the inverse of this I theta. Okay, now and then because that this is just a diagonal matrix, so remember the inverse of any diagonal matrix is just what you take the reciprocal of each of these diagonal entry, so that you will get something like this. Okay, as your inverse. Okay, or of course you can use, of course if you don't have this results, so of course you can use the traditional method and find the inverse. Okay, now never mind. So after this, then now we can go back to the determination of the distribution of the mu hat. Okay, so here just recall our mu hat follow the normal distribution with the mean mu and then the variance equal to sigma 1 1. So which is what? So sigma 1 1. Okay, so remember sigma 1 will be what? The first diagonal entry of the covariance matrix. Okay, so which is equal to sigma square over n. Okay, now and here in order to continue our game, okay, so then we consider what? We consider this standard score. Okay. Okay, so which follow the standard normal. Okay, and then here we would like to find the ZL and ZU such that this probability is so it's equal to 98% probability, right? Okay, now and here so if you want to find this ZL or ZU, okay, so remember we will focus on what? We will focus on the symmetric confidence interval. So that means we want to have 98% in the middle, okay, and then 1% on the left, 1% on the right. Okay, and then here just using the normal distribution table, then you get these two critical number, isn't it? Now and then here once you got this, so you can just put that in, okay, and then you will get something like this. Okay, and then the mu is 6.1379. Okay, now but of course here this one is not useful is in getting the confidence interval for mu, because here so one trouble here is because there is still an unknown, okay, which is your sigma square here, okay, which is the true value of the sigma, and definitely this is something which is so long, right? Okay, now so of course here where you have two unknown appear in the same identity, same inequality, then you cannot find this range of the mu, right? So here in order to move on, so it seems like that you have to pick up something to replace this sigma square, and then one possible solution is so you try to replace the sigma by sigma hat square. Okay, so which is equal to 1.9305. Okay, so that's why here then I try to approximate this variance by this sigma square over n, which is equal to 0.0965. Okay, now and then once you have this, okay, then of course you can try to continue the calculation. So you just solve this inequality for the mu, so then you will obtain that the mu will be between 5.41 and up to 6.86 with probability 98%. Okay, then that will be the confidence interval that we are looking for. Okay, now but here, okay, just one thing that I need to alert all of you is so here in order to find the confidence interval for mu, so we try to do the approximation by replacing the sigma by the sigma hat square. Okay, of course mathematically, so this will this will lead to some estimation error, because if you replace the sigma by the sigma hat, so actually this number may not necessarily follow the standard normal, okay, but just perhaps for if your sample size is sufficiently large, so it will be approximately normal, and then so this estimation error will be small. Okay, but here, of course, in this situation, so it looks like that if we do not do this approximation, it looks like that this inequality will be impossible to solve. So that's we have no choice, okay, but just to adopt this. Okay, but of course, in practice, so you can only use this approximation only when your sample size is sufficiently large. Okay, so this is something you have to be careful. Okay, now anyway, so then this is how do you get the confidence interval for the meal. Okay, and then here you can also do the same calculation for the sigma as well. Okay, now so here, in order to find the confidence interval for the sigma, so again, then you consider the distribution of this estimator of sigma, which is your MLE. So again, just like what we did for the mu hat, so the sigma hat will follow the normal distribution with mean, mu, and then the variance sigma 2,2. Okay, and then here, so the sigma 2,2 will be what? Will be the second diagonal entry of this covariance matrix, isn't it? So which is the sigma square over 2n. Okay, now and then here, so given this, so you can now to construct the confidence interval, so just like what we did for the earlier example, so you consider the standard score. Okay, which follow the standard normal, and then you try to find the ZL and ZU such that this probability equal to 98%. Okay, and then again, just like what we did earlier, so ZL and ZU just equal to minus 2.33 and 2.33 respectively. Okay, now and then once you have that, so you punch in the sigma equal to square root 1.9305. Okay, and then you can solve this inequality for the sigma. Okay, now of course here, without doing any further estimation, of course you can still solve for the sigma. Okay, but of course here, you may still, okay, in case if you don't want to do the want the things become too messy, so of course you can still approximate this sigma square by the sigma hat square. Okay, so which is the things that I do here. Okay, so in that case, so if we replace the sigma square by the sigma hat square in the calculation, then this will be the confidence interval that you are going to find. Okay, so I guess I'm not going to do that, so you can try to work it out by yourself. Okay, now but of course here, of course if you do not do this approximation, so you can still find this confidence interval. Okay, because it will just a linear equation for the sigma, so it's still solvable. Okay, of course if you want to get a precise answer, so you should just solving this inequality, okay, and get the most correct answer, most accurate answer. Okay, so here, okay, then this is the example 29, just telling you how do you find the confidence interval for the parameter when your distribution has multiple parameters. Okay, so actually the procedure is just same as what we did before, but just when you get the variance of your individual parameter, so you have to first obtain this covariance matrix, okay, of this of all the parameter first. Okay, so here then this is the example 29. Okay, now so once we have some idea about how to estimate the parameter in your distribution function, then now we can try to use it, okay, to study our loss model. Okay, so for example, okay, so let's say if you got a loss amount in an accident, so which follow certain distribution. Okay, so let's say in this example, so so it has a normal distribution with the mean with the parameter mu and sigma. Okay, And then so let's say when I want to evaluate the losses, okay, so I'm interested in knowing the expected value of it. Okay, now then as we know, okay, so for normal distribution, the expected value of it is just equal to exponential to the power mu plus sigma square over 2, isn't it? So where the which involve the parameter mu and the sigma. Okay, now and then of course in order to get this exact value, then you have to know the values of the sigma and the mu, isn't it? Okay, then of course to do that, then we can try to estimate it using the random sample, isn't it? And then here given this random sample, then you can try to estimate the get the estimate on the mu and the sigma. Okay, so which is done by the maximum likelihood method. Okay, and then here once you get the estimate of this mu hat and the sigma hat, then now you can try to estimate the expected value of x through this simple approach, through this formula. So simply replace the mu and the sigma by your MLE. Okay, then you will get your estimate on your expected value. Okay, so then this is how we do the estimation. And then of course another example can be about the King frequency. For example, let's say I have so let's say okay, the King frequency in a certain insurance policy has a Poisson distribution with the mean lambda. Okay, and then here our target is, so we want to estimate the probability that you have at least 2 claims in this insurance policy. And then here so given that it follow the Poisson distribution, so we know okay, this probability is just equal to 1 minus equal to 1 minus probability that n equal to 0 minus probability that n equal to 1. Okay, so I guess this is something you know how to do that. Okay, then given that it follow the Poisson distribution, so then this is the probability. Okay, so which is what involve the parameter lambda. Okay, then here in order to get the exact answer, then just like what we did for the previous example, so again then you try to do the sampling, right, and get the sets of the sample value of this n, and then you use the maximum likelihood method and estimate the lambda, right? Okay, and then after this, then you can just put that in this formula, then you can get your estimate on this probability. Okay, so this is how do you estimate your target expected value and the probability using this maximum likelihood estimate of the parameter. Okay, now but here one question that people will ask is will be the accuracy of this estimate. Okay, is it accurate? Now why it is so? Because here when we try to estimate this true quantity, so we replace the true parameter by the MLE. Okay, and remember the MLE is estimated from what? From your random sample, right? And because this random sample it's just a small sample randomly drawn from the distribution. Okay, so here then this case this MLE will have some error as well. Okay, or some randomness. Okay, and of course because of that, so if you try to use the MLE to estimate your expected value or maybe the probability, then that means this estimate may not necessarily to be accurate, in the sense that it may be different from the true value. Okay, so because of that, so one question people will ask is, so what is your error of estimation? Okay, so which is what your mean square error of this estimator. Okay, one thing. The second thing is, so because this point estimator may deviate from the true value, of course the next question people will ask is, so is it possible for us to get the range of the true value of this expected value or maybe the probability? Okay, meaning that I want to find the confidence interval for that. Okay, so then this is something that we want to do. So how do we do this? Okay, so let us try to formulate the problem as follow. Okay, so here let's assume that I got some random variable that I'm interested. Okay, and then it follows certain distribution of with some parameter theta. Okay, now and then here, so we let the g theta to be the function that I'm interested to study. Okay, so which is a function of the parameter. So of course in general, so it can be anything that you like. So for example, it can be the expected value of s, okay, or maybe the certain probability. Okay, so remember, so this thing is also the function of your parameter. Okay, so let's say in the earlier example, so let's say for the first example, which the loss amount follow the not normal distribution, so the expected value will be a function of the mu and the sigma. Okay, and then for the second example, we about the king frequency, so the probability is also a function of your parameter. Okay, so then this is what the g theta is about. Okay, now and here to estimate this g theta, okay, so we use the maximum value estimate. So we let the MLE, we let the theta hat to be my maximum value estimate of the theta coming from maximum value method. And then remember, given this theta hat, then you try to estimate the g theta by the g theta hat. Okay, then this will be our estimator. Okay, now and then here remember our goal here is, so we want to study two things. First will be the error of this estimator, right? Okay, so which is your mean square error. And then here, in order to investigate this mean square error, so you have to know so what will be the variance of it, and of course also the bias as well. Okay, first thing. Another important thing is, so because the g theta hat may be deviate from the true value, then of course another thing is, so we want to find so what is the range of the true value of this g theta. Okay, meaning that I want to find the confidence interval for this. Okay, now but of course as we know, so in order to do this, okay, so you have to know what is the distribution of the estimator. Okay, all right, so here, okay, in order to achieve our two goal, okay, so then what you need to do is, so you have to know what is the mean square error of this estimator. Another thing is the distribution of this estimator as well. So to get the distribution of this g theta hat, so first of all we know, so this estimator is driven by this MLE, isn't it? And then as we know, so when the sample size is sufficiently large, so this MLE will follow a kind of a normal distribution, right? Okay, so given that it follows the normal distribution, then you can try to say something about the distribution of the function of the MLE. Okay, so in fact, so provided that your G is sufficiently smooth, okay, in the sense that it can be differentiable several times. So actually we can show that so this G theta will follow the normal distribution as well. Okay, so here then this is what this theorem is about. Okay, now and then here, okay, because for given a distribution, so we may have one parameter, we can have multiple parameter. All right, and then because of that, so I will try to divide this theorem into theorem 1 and theorem 2. Okay, so for theorem 1, it will be for the single parameter case, and then for theorem 2, okay, so that will be for the multiple parameter. Okay, and here because we in our loss model, so we only have the distribution with two parameter, so I will just concentrate on two parameter case. Okay, so And actually, okay, so the derivation is very similar, but just the result may be slightly different. Okay, so that's why I just divide these two theorem into two parts and analyze that one by one, so that will be easier. Okay, now so here let us go back to the single parameter case. Okay, so let's suppose we got a distribute. So we let the fs be the probability density function of some random variable s, and with one single parameter theta. Okay, and let's suppose this PDF satisfy the regularity condition specified in the log theorem 1. Okay, it should be property free. Okay, in the earlier session. So that means the fs is 3 times differentiable. You can integrate the order of the differentiation and the integration or stuff like that. Okay, so actually this condition just guarantee that so your MLE follow the normal distribution. Okay, remember, so this is one of the key steps, okay, in getting the distribution of this function of MLE. Okay, so we need to have this MLE to have a normal. So because of that, so you need to have your fs satisfy the regularity condition so that the probability free will hold. Okay, now and then here let's suppose that let me let the g theta to be my function, so which is twice differentiable in theta. Okay, and then so we let the theta n hat as MLE. Okay, then this theorem says that when n tends to infinity, then this random variable g theta n hat will has approximately normal distribution with the mean equal to the true value, okay, g theta, and the variance g prime theta all square, okay, which is your first derivative all square divided by I theta. And remember, I theta is just equal to minus n expected value of second derivative of the log of f is theta. Okay, so then this is this theorem is about. Okay, so it tells you the distribution of this estimator, which is normal, and it also tells you the variance as well. Okay, so here remember, so given this variance, of course you can also talk about the mean square error of your estimator. Okay, so remember this will be equal to what? Variance plus the square of the bias. Okay, but as we know, when n tends to infinity, so this estimator will has the mean g theta. So meaning that, okay, you take the limit. Okay, so that will be equal to g theta. So that means that it will be asymptotically unbiased, so that this bias will be gone. Okay, and then here the variance will be equal to g prime theta over I theta. So that means that the mean square error of this estimator will be just equal to this number. Okay, so here actually this theorem will try to give you the answer for that two questions. Okay, now then the next thing is, so how do we prove that? Okay, now so first of all because this is a function of the MLE. Okay, and then here provided that the fs satisfy the regularity condition, so according to the probability free, so we know, so your MLE here will have the approximately normal distribution with mean theta and the variance 1 over I theta. Okay, so this is our starting points. Okay, now then the next step here is, so we need to find the distribution of this g theta n hat. Sorry. Alright, now so remember to find the distribution of certain random variable, then of course the best solution is you need to get the formula of this g theta n hat. Okay, and then you try to analyze it carefully. Okay, and then here, because the g is a function of your MLE, and you know the MLE has normal distribution, right? Then what we do is we want to obtain the formula of this g theta n hat in terms of the theta n hat. Okay, now but of course apparently it will be very tricky to do so because you don't know what is the exact values of the function g. Okay, so here in order to obtain this formula, then the only thing that we can do is we can only do it by brute force. Okay, so what do we mean by brute force? That is, we will try to get this formula through the Taylor expansion. So remember, for Taylor expansion, so if you have any function fx, okay, so you can use the Taylor expansion and try to rewrite this function as a kind of polynomial of x, right? Isn't it? Okay, so you can try to obtain this formula. Okay, now so here then what I do is, so I will try to apply this Taylor expansion to this g theta n hat and expand it, okay, in this way. Okay, now so here, okay, then I take the f to be g, and then for the s, so I will take this to be theta n hat, okay, and this will be your g. Okay, and then for the a, which is your reference spot, so I will take the a equal to theta. Okay, and then here after you take this, so and apply the Taylor expansion, so then this is what you get. Okay, now and then here just be careful that, so because the g is only twice differentiable, meaning that it can only be differentiated twice. Okay, so that here you can only stop at the second order term. Okay, and then of course by stopping at this point here, just be careful. So so for the second derivative of g, so the function value is taken at some arbitrary point c, so which is some point between theta n hat and theta, so which is what is suggested in the Taylor theorem. Okay, but nevertheless, forget about this technicality. Then at least then we have some formula, okay, for the g theta n hat. And here we are able to express it in terms of what your MLE. Okay, so all these MLE are pushing out. And then here, because your theta n hat has normal distribution, then you can try to get the distribution of this g theta n hat by analyzing the formula on the right. Okay, now but and then how do we do this? So first of all, so for the first term, so this is just a fixed number, right? Okay, and no random number. Okay, then this is something we don't need to worry. Now, and then the next thing is, then we try to consider the last term, because the last term is very complicated. Okay, not to mention you have the theta n hat all square. So the worst thing is, so you also have some unknown number g double prime c. Okay, so remember the c is somewhere between theta n hat and theta, right? Okay, so here, so we need to handle this, okay, at our first priority. Now, how do we get this? So here, first of all, because your theta n is your MLE, right? And remember this, so MLE is consistent, so meaning that when n tends to infinity, MLE is getting close to the true value. And then because of this, okay, so then this guy will be tends to 0. Okay, then of course we will expect this whole term, okay, maybe getting close to 0, right? Now, but of course in order to argue this it will tend to 0, so we still need to argue that whether this term will just remain to be a finite number or maybe something belong to infinity. Okay, but here, okay, if here, okay, because this c, okay, is somewhere between theta n hat and theta. Okay, and so when the n tends to infinity, theta n will be getting close to the theta. And also because your function g is twice differentiable. Okay, so meaning that okay, so this g double prime s is always exists. Okay, so meaning that when your theta n hat pushing close to the theta, so this g double prime c will not belong to infinity, so it will only getting close to the g double prime theta. Okay, now and then in that cases, okay, so then this will be bounded so that this number will be getting close to 0. Okay, of course this is just a very rough argument anyway. Okay, now and then so at least this term will be gone. Now then we just need to handle this the first two term only. Okay, now then here then we remain to look at so what happened to the first term. Okay, now so first of all in this term so it involves the random variable theta and hat. Okay, and then according to what we said earlier, so it followed the normal distribution with the mean theta and then the variance 1 over I theta. Okay, now and then given this, then it will imply that if you consider the theta n hat minus theta, then it will follow the normal distribution with mean 0 and the variance 1 over I theta. Okay, now and then so then this one will has what normal distribution with mean 0 and variance I theta. Okay, now and then given this, so and then if we try to look at the whole term, okay, so actually it will be just a constant multiplied by the normal random variable. Okay, then according to the property of the normal distribution, then these products will follow the normal distribution with the mean 0, and then the variance will be g prime theta all squared divided by I theta. Okay, and then now you try to add a constant in front of it, which is g theta, then this will imply that so this g theta and hat will follow the normal distribution with mean g theta. Okay, and then the variance remain unchanged. Okay, so then here then we are done. Okay, so we shows that so this g theta and hat. Okay, sorry, so it should be g theta and hat. Okay, so we'll follow the normal distribution with the mean equal to g theta and the variance equal to this number. Okay, then it proved our theorem. Okay, now so then this is so basically a kind of a rough proof of this theorem. Okay, now and then here so this is a single parameter case. Now and then here let us try to apply the same trick and work on the two parameter cases. Okay, so here okay we will consider a two parameter cases, and let's suppose I got a function of this two parameter which is a twice differentiable. Okay, so here assuming that okay so your distribution function satisfies the regularity condition, then we are able to show that when n tends to infinity, then this estimate okay g of this MLE will has approximately normal with the mean equal to the true value. Okay, and then the variance will be equal to this fancy number. Okay, and here the matrix in the middle is just the covariance matrix of your MLE. Okay, and remember that okay so that will be equal to the inverse of this matrix I theta. Okay, now anyway so then this is what the theorem 2 is about. And then if you want to prove this theorem, so I would say the proof is parallel to the single parameter case. Okay, but just the calculation may be a little bit complicated. Alright, now so just let me quickly run through this proof. Okay, now first of all, assuming that the distribution function satisfies the regularity condition, then when n tends to infinity, then the pair of your MLE will follow the multivariate normal distribution with mean equal to the true value of the parameter, and then the covariance matrix equal to that. Okay, and here okay so just remember that this covariance matrix is just equal to the inverse of this matrix I theta. Okay, now anyway so here then let us try to use this okay to get the distribution of this estimator. Okay, now and then again in order to get the distribution of this estimator, then we try to obtain the formula of that using the Taylor expansion. Okay, now and then here because you have two you have two parameters, so meaning that your function has two variables. Then we will try to use the multivariate version of the Taylor expansion. Okay, so just recall. So given that you have a function of two variables x and y, then so assuming that it is differentiable, okay, then you have this Taylor expansion for this function sy, so which is equal to this. Okay, so need to be fancy. Okay, so then this is the two so the Taylor expansion for some function of two variable. Okay, so I would say actually this Taylor expansion is very similar to the case for the single variable. Okay, so again, so we first have this FAB, so which is same as the FA in, so which is same as the FA, okay, in your Taylor expansion of FS, okay, one variable case. Okay, but of course, and then here besides this, okay, so it contains the first order term, okay, so which is the red term here. Okay, so actually this one will correspond to the first order term. Okay, and here because given a function of two variables, so you have two different first derivatives. So one is a partial derivative with respect to s, another one is partial derivative of y. Okay, and then for the this free term, okay, so then that will be the second order term, so which is parallel to the second order term that we have here. Okay, then this will be the Taylor expansion for function of two variables. Okay, and here we will try to use that to obtain the formula for this estimator. So what you do is so you take the fxy to be your g theta 1 hat theta 2 hat, so meaning that your x and y will take the value as theta 1 hat and theta 2 hat, and for the reference point AB, then you take the AB equal to theta 1 and theta 2. Okay, so given this, then this is what you have. Okay, and again, just like the earlier cases, so we can only expand this Taylor expansion up to the second order term only. Okay, and so then this is what you get. Now, and then here, in order to move on, so of course the first thing that you should do is, so you try to simplify this expression a little bit first. Okay, because it involves so many terms, right? Okay, so here, just like what we did for the theorem 1, so we can first consider the second order term first. So, okay, so which has something which is very complicated. And then here, just like the single parameter cases, so the MLE is consistent. So in the sense that theta 1 hat will getting close to the true value, theta 2 hat is also getting close to the true value. So meaning that this 1, 2, 3 will all getting close to 0. And again, because of the because the G is twice differentiable, okay, and this C1 and C2 will be getting close to the theta 1 and theta 2, so meaning that this function will be sort of bounded. Okay, and in that cases, okay, so it will, so this 3 term, okay, will be getting close to 0. Okay, so that you can forget about that. And now, okay, what you need to do is just to get the distribution by analyzing the first 3 terms. Okay, so again, the first term is just a fixed number, so we don't need to worry too much. Okay, so then we just need to analyze the last 2 terms, which involve the MLE. And then here, to facilitate the analysis, so I will try to combine the last 2 terms into this matrix product. Okay, now, and then here, so what we will do is that. Okay, now, so here, remember, when n tends to infinity, then this theta 1 hat and theta 2 hat will follow the multivariate normal distribution. okay, with this with the mean equal to the true value, and then the covariance matrix equal to this number. Okay, now and then given this, then you can easily argue that, so if you consider the differences, okay, difference between the true value and the MLE, and this one equal to this vector minus this fixed vector, right? And then according to the property of multivariate normal, so it will follow the multivariate normal with the mean equal to 0 vector. Okay, so just subtract this one with the mean, and then the covariance matrix sigma. Okay, so that means this guy will follow the multivariate normal. Is that okay? Now, so then given this, then you can now try to use the property of the multivariate normal and argue the final distribution of this estimate. Okay, now first of all, because this is a multivariate normal, then it will imply that. So it will imply that, so your this function okay, so if you compare this term together, so this one will follow the multivariate normal with the mean equal to 0, and the variance will be A sigma A transpose, isn't it? And then of course if you expand that, so this one will be equal to this matrix. Which is border. Very, very complicated. Okay, now so then this is what you get for this second term. Okay, now and then here if you try to add one more term in front of it, okay, one more term in front of it, then again by the property of the multivariate normal or normal distribution, so then this sum, okay, will has what normal distribution with the mean equal to g theta 1 theta 2, okay, and then the variance remain unchanged. Okay, so here, okay, then we are done. So remember this one is just equal to your value of the estimator, then it will follow this normal distribution with the mean equal to this true value, and then the variance will be equal to this number. Okay, then this proof our theorem. Oh, alright, so here, okay, then this is basically what, so basically so the proof of this theorem. Okay, then of course using this, then you can now try to use this result to find the mean square error of your estimator. Okay, and of course you can also use that to find the confidence interval for the true value of this function. Okay, and then here, then this method will be what we call the delta method. Alright, so basically just a method that helps you to find out the confidence interval of a function of parameter. Okay, is that okay? Now and then here then this is the theoretical part, and now let us try to look at some numerical example and just have some quick practice on this delta method. Okay, now and then here in example 30 we consider this scenario. Now so let's suppose the losses in a traffic accident follow the Pareto distribution. Okay, and then with certain parameter alpha, and then the theta equal to 500. Okay, so which is given to you. Okay, then the only parameter will be the only unknown parameter will be your alpha. Okay, now and then here in this example, so our goal is we want to estimate the probability that the loss amount is greater than 1,000. Okay, so then this is what we want to do. Okay, now of course here, given that the S follow the Pareto distribution, of course you can get this probability by computing this integral. So you just integrate your PDF, alright, for Pareto distribution, and then you integrate from s equal to 1,000 up to infinity. Okay, and then here, so just after some calculation, so you will get this integral equal to this guy. Okay, and then equal to let me see, so 1000 plus theta over theta to the power alpha. Okay, and here because theta equal to 500, right? So then that will be, this one will be 500 divided by 100, 50, and then to the power alpha. So which is equal to 1 over 3 to the power alpha. Okay, so here then we see, so this probability will be a function, will be a function of alpha. And here, because the alpha is unknown, so in order to get this probability, then you have to estimate this alpha. Okay, and then to do that, so we try to take out a random sample of size 500. Okay, and then here, okay, then I try to use this to analyze the alpha. And then here you are given that, okay, so the sum of this number, okay, will equal to 194.679. Okay, so which is the number that you get from the random sample. Okay, now and then given this, so what I want you to do is, so I want you to use the delta method and find the confidence interval for this probability. So that means I'm interested in looking at the range of this probability. And then I want this to be true with 95% probability. Okay, so then this is what I want to do. Okay, now and here how do we do this then? Okay, now so then here let us first try to scratch the outline of our solution procedure. Okay, and just have some picture, okay, on what should we do. Okay, now first of all, according to our earlier calculation, so this probability is equal to 1 over 3 to the power alpha, right? So which is a function of G alpha. Okay, now and then here, in order to get this confidence interval, so what do we need? So we need the G alpha hat, right? Okay, so which is what your point estimate of G alpha. Okay, and of course here your alpha is your MLE. Okay, first way. And then of course the second thing will be, so in order to get the confidence interval, so you need the distribution of your G alpha. Okay, in order to for the construction of the confidence interval. Okay, so here, okay, then in order to find this confidence interval, then we will first obtain the maximum likelihood estimate. We want to obtain this G alpha hat, which is the MLE of this maximum likelihood estimate of this probability. And then second, we will construct the confidence interval by obtaining the distribution of this G alpha hat. Okay, now so here then let us try to do that one by one. Okay, now so here, in order to get this estimate, so you have to get what is the MLE of this alpha. Okay, now then to do that, then we try to use the maximum likelihood method. Okay, now so remember to do this, so we first try to consider the likelihood function. Okay, so which is what the product of this stuff, right? Isn't it? Okay, so which is the probability that S1 equal to S1 dot S500 equal to S500, right? Okay, and then of course here, in order to find the maximizer, so we will try to consider the log of this likelihood function. Okay, so which is the log likelihood, so that will be, so after you take the log, then that will become the summation. Okay, now and then here to move on, so you can substitute the PDF of the Pareto distribution. Okay, and then when you take the log, and then you can break down this one into into 3 terms. Okay, so then this is what we have. Okay, now then once you have this log likelihood function, then the next step is, then you try to find the maximum likelihood estimate of this alpha. So remember, we will try to get this by choosing the alpha that could maximize your log likelihood function. So to do that, then you try to consider the first order condition. Okay, then you just differentiate your log likelihood function set equal to 0. Okay, so here so for the first one, which you have the natural log alpha, so that will become 1 over alpha. Alright, and for the second term, so you only have a single alpha. Then when you differentiate that, then you only have the natural log theta. And then for the third one, so you differentiate that, so you only get natural log xi plus theta. Okay, now and then here, in order to move on, okay, so here then let me try to put all the term involving alpha on the left and then all the relevant term to the right. Okay, so here then I try to put these two terms to the right, so then this is what you get. Okay, and here for the first term, so you have the summation of this 1 over alpha, and you have 500 copy, so then this is what you get. Now and then here, then you can try to solve this equation for the alpha, so then this will be what's the final formula for your MLE. Okay, now then the question will be, so what will be this number is about? Okay, now and then here, according to the given condition, so we know, so this summation of this log of 1 plus xi over theta is equal to 194. Okay, so that you can just put that in. Okay, then you will get the alpha will be equal to 2.568477. Alright, so then that will be your MLE. Now of course here you should also check the second order condition, but here I just try to save space and I didn't do that, so you can try to verify that by yourself. Okay, now then this is how do we find the MLE of the alpha. Okay, so here then once you get this MLE, then now you can try to calculate this G alpha hat. Okay, so which is equal to equal to 1 over will be equal to 1 over 3 alpha, and then the alpha you punch this number into that. Okay, and then you evaluate that, then you will get the probability will be equal to 0.059501. Okay, so which will be what your maximum likelihood estimate of your probability. Okay, then we finish the first step. Okay, now so then what is the next step there? Now so here the next step is, so in order to construct the component interval, so you also need to know what is the distribution of this G alpha hat. Okay, and remember that so because the alpha hat is the MLE and your sample size is sufficiently large. Okay, so here according to the theorem number 1. Okay, according to theorem number 1, okay, so your G theta n hat will has approximately normal with the mean G theta and the variance G prime theta all squared divided by I theta. Okay, so let us try to use these results. Okay, so your G theta will follow the normal distribution, okay, with the mean equal to G alpha, and then the variance will be G prime alpha all squared divided by I over alpha. Okay, and here I alpha will be equal to minus n expected value of the second derivative of this log of f with respect to alpha. Okay, now so here, okay, in order to move on, okay, so it looks like that you need to compute this you try to obtain this number. Okay, so first of all you can first compute this I alpha first. Okay, so which is equal to minus n of this expected value of this second derivative. Okay, now so again to compute this expected value, so first of all you first substitute the PDF of your f. Okay, so which is equal to alpha over x plus theta alpha plus 1. Okay, then you can put that in, and then once you take the log, then you can break down into 3 parts. Okay, and then the second step is you try to differentiate this respect to the alpha twice before you take the expected value. And here you can see that after you differentiate this one twice, so these two terms will be gone. Okay, and then you only have the first term left. So this one you differentiate twice, you get so minus 1 over alpha square. Okay, now and then once you have that, and because this one has nothing to do with s, so once you take the expected value, actually it doesn't change the result. So here, okay, then so this one should be 500. Okay, then and then so after you take the expected value, so you will get this is equal to 500 over 8 alpha square. Okay, then you get the I alpha, which is your denominator. And then on the other hand, you can also calculate your G prime alpha as well. Okay, so remember your G alpha is just equal to 1 over 3 alpha. Okay, then if you differentiate one time, okay, so then that will be 1 over 3 to the power of natural log 1 over 3. Okay, so remember why we have that. So actually it's just due to the result that if we differentiate a function which is a to the power s respect to s, so that will be equal to a to the power s times natural log a. Okay, and here, okay, so we take the a equal to 1 over 3 in the calculation, and then the s will be your alpha. Okay, so here, okay, then you will get this G prime alpha. Okay, so that you can get your variance. Okay, now and then given this information, then now you can try to construct your component interval. Okay, now but and then here, okay, to do this, so we recall that so your G alpha hat follow the normal distribution with the mean equal to G alpha, and then the variance is a G prime alpha all squared divided by I alpha. Okay, and given this, so we know the standard score, okay, which is G alpha hat minus the mean divided by the square roots of the variance follow the standard normal. Okay, and then to construct the component interval, our goal is we want to find the Z and ZU such that this one is true for 95%, isn't it? Now and then here to get this so to get the Z and ZU, so again we are looking for the symmetric component interval. 95% in the middle, 2.5% on the left, 2.5% on the right. Okay, then you get this ZL equal to minus 1.96, this ZU equal to 1.96. So that's here, then you got this true number. Okay, and then here, so you also know the this G alpha hat is equal to 0.059501. Okay, and then here so our target is we want to find the component interval for the G alpha, so which is here. Then what you need to do is you try to solve this inequality for this G alpha. Now, but of course here one trouble is, so it looks like that so we still encounter some extra unknown in this inequality, that is the denominator. Okay, so which is equal to what? The square root of the variance of the G alpha. Okay, and then here you can see, so it requires the value of the true value of the alpha. Definitely this is something that you don't know, right? Okay, so here in order to solve this inequality for the G alpha efficiently, so what we do is we have to do some approximation. So in particular here, so we will try to approximate this variance by replacing all the alpha by alpha hat. Okay, so that you get this approximation of the variance. Okay, and then here if you replace the alpha by the alpha hat, and you know the alpha hat already, so you can just punch in into the formula, okay, that we obtained above, so you can obtain this variance equal to this number. Okay, so you can try to do this by yourself. Okay, now and then once you have that, then you use that to replace the denominator. Okay, so that then this is what you get. Okay, so you replace this variance by this estimate. Okay, then now your inequality will only involve one unknown G alpha. Then now you can try to solve it, and then you will get the G alpha will be between these two numbers. Okay, and then given this, then you can conclude that this 95% confidence interval will be 0.044784 and 0.074218, and this prediction is true for 95% probability. Okay, so here and this is how do we find the confidence interval for the function of some unknown parameter in your distribution function. Okay, and here I just want to bring out one important technical remark is so quite often if we want to find the confidence interval for the function of the parameter, so one trouble here is so your denominator, okay, which is the square roots of the variance, is usually a very complicated function of the true value of the parameter. Okay, and here in order to find your confidence interval successfully, so usually what we do is we will try to approximate the variance, okay, by replacing the alpha by the alpha hat in the formula. Okay, so that means here, so we will try to do this approximate. Okay, so that this variance will become a number, so that then this inequality will be very easy to solve. Okay, so then this is the trick that we always use, okay, in this delta method. Okay, now so here then this is the example 30. Okay, and now let us try to look at one more example, okay, which is just a continuation from the example 30. Okay, and here we use the same setup as in example 30, and here we will try to study this problem. So let's suppose we consider an insurance policy that covers these losses in the traffic accident. And here you know that so this policy will has a deductible 100, and other than that, so there is no co-insurance or the policy limit. Okay, and then what we are interested to know is, so I want to know what is the expected value of the YL, so which is the expected claim payment made by the company in loss events. Okay, now and then here what I want you to do is, so given the sample data that you obtain, okay, so I want you to find the confidence interval of this expected value of YL, and then I want you to find the 98% confidence interval. Okay, now so then how do we get this then? Okay, now so first of all so this expected value definitely will be a function of the alpha. Okay, because your YL is just equal to the maximum of the x equal to 100 and 0. Okay, if you have the double. Okay, so here then if we take the expected value of that, okay, and then this expected value will depend on what? The distribution of S. And then here, because it follow the Pareto distribution with parameter alpha and theta equal to 500, so of course we will expect, so that should be a function of alpha. Okay, now and then here given this, so in order to get your confidence interval, then basically we can just follow the procedure as we did in the earlier example. First of all, you try to obtain G alpha hat, isn't it? Okay, so your point estimate. Okay, and then the second one will be what? The distribution of the G alpha. Okay, so we try to do it in two sides. Okay, now so here, okay, let us try to do that one by one. Now first of all, you first need to obtain the exact formula for this expected value of YL, so which will give you the function G. Okay, so here first of all, just recall under if you just have ordinary number 100, so the YL is just equal to the maximum of x minus 100 and 0. Okay, and remember that to calculate this expected value, so you can use the formula in topic 2, and then you can break it down into the difference of two expected value, which is equal to the expected value of s minus the expected value of minimum s and 100. Okay, now and then here using the table, using the table that I give you. So for Pareto distribution, so expected value of s equal to this number, and then expected value of minimum s and 100 will be equal to this number. Okay, and then here, so you can substitute theta equal to 500, which is something that you know, then put that in, simplify the stuff, then this will be the formula, okay, for the expected value of YL, which is equal to the G alpha. Okay, then we finish the first step, and then the second step is, so you try to obtain the G alpha hat. Okay, and here remember in the early example, so we find that so your MLE of the alpha is just equal to 2.56x477. Okay, then you just put that into this formula, then you can get the G alpha hat successfully, which is equal to 239. Okay, now and then here, then we finish the first step, so we get the point estimate of the G alpha. Next, we will try to obtain the confidence interval by first finding the distribution of the G alpha hat. Okay, and here again, because the alpha hat is your MLE. Okay, and then here you can see this function is very nice function, twice differentiable. Okay, so here then you can just use the theorem 1 again. Okay, so your G of alpha hat will has approximately normal distribution with the mean equal to G theta and the variance equal to G prime theta all squared divided by I theta. Okay, so let us just try to apply these results. Okay, so which is here. Okay, and here again, so in order to move on, okay, so you have to compute, so what is this G prime alpha and the I alpha. Okay, and here just recall in the example 30, so we already get this I alpha already, so the I alpha equal to 500 divided by alpha square. Okay, so which is from example 30. Okay, so then the next step will be your first derivative of G. Okay, so which is your G prime alpha. Okay, now and here, so given that your G alpha is equal to this fancy expression, okay, then you just try to differentiate it one time and use the product rule, then you will get the first derivative. Okay, so here then given this, then you can easily obtain your variance will be equal to G prime alpha all squared divided by I over alpha. Okay, now and then of course in the context of finding the confidence interval, so as I have said in the early example, so we need to try to approximate this variance first, okay, by number, okay, so that we don't have very fancy inequality. Okay, now and then here what we do is that you try to replace all the alpha by alpha hat. Okay, so that here then by substitute alpha equal to alpha hat into this formula, then you can get the variance can be approximated by this 508.7221. Okay, so then that will be the approximation formula for your variance. Okay, now and then given this, then now you can start to construct your confidence interval. Okay, so remember that so your G alpha hat follow the normal distribution with the mean G alpha, and then the variance is G prime alpha square over I alpha, isn't it? So that means your sin score Okay, follow this standard normal. Okay, and then what we do is we try to find the EZ and EZU such that this one will be valid for 98%. Okay, and again, to find this EZ and EZU, so we will try to consider a symmetric confidence interval, meaning that you want to have 98% in the middle, 1% on the left, 1% on the right. Okay, and then here then you will find that EZL and EZU will be 2.33. Okay, so that then you can put that in. Okay, and then here so your G alpha hat will also be equal to, let's say, 239.5958. So let me see, 239.4958. Okay, and here in order to solve this inequality for alpha, remember we try to approximate this variance by this number as well. Okay, so after you have made all this preparation, then that will be the inequality that you are going to solve. Then just by solving this inequality for the G alpha, then you will find the G alpha will be between 186.943 and 292.0486. Okay, and this prediction will be true for 98% probability. Then that will be your confidence interval for your expected cost per losses. Okay, so here then this is just another example on how do you find your confidence interval for your function of parameter using this delta method. Okay, so hopefully you guys can understand the whole procedure. So actually the procedure is just so first of all, given your target, so you first try to obtain your point estimate of your target, okay, using the MLE of your parameter. Okay, so then this will include, first of all, you obtain the formula for your target, which is your G alpha, and then by getting the MLE of your parameter, then you get this estimate. Okay, and then the second step will be, so to construct the confidence interval, then you try to find the distribution of your estimate. So according to the theorem, so this will follow the normal distribution. Okay, and then after this, then you can set up your probability like that, okay, and find your critical value is at U, and then at the same time you will also approximate the variance by putting the alpha equal to the MLE and then estimate your variance. Okay, so that you can find your confidence interval successfully. Okay, so here then this is just his summary on the procedure of finding this confidence interval. Okay, now and then here in the previous two example, so we just focus on the case when we have a single parameter. Now and perhaps here before we start, so let us look at another example which you have two parameter cases. Okay, so here in the example 32, so we have the case that the loss amount has a normal distribution with the parameter mu and sigma. So here you have two parameter scenario. Now, so let's suppose that, okay, so the MLE of the mu and the sigma is equal to the mu hat equal to 4.215 and the sigma equal to 1.093. Okay, so which is the number that we obtain by considering the random sample of size n. Okay, so here, okay, so so let's assume that I have performed the analysis already. Okay, and then at the same time, I also estimate that so the covariance matrix of this mu hat and the sigma hat will be equal to this sigma equal this diagonal matrix. Okay, so again, so this value is estimate from your random sample. Okay, now so here this is the basic information, and what I'm going to do is, so I want you to use this information, assuming that the sample size is sufficiently large, then I want you to obtain the confidence interval, 95% confidence interval for the expected value of S. Okay, so here then how do we do that using the delta method? Okay, so then basically the procedure is just same as what we did for the single parameter case. Okay, so first of all, you first try to get the formula for the expected value of S. Okay, so here, okay, as we know, so if S follow the log normal distribution, so the mean will be exponential to the power mu plus sigma square over 2. Then that will be what? Your function G, mu, and sigma. Okay, and then the second step will be, so you try to obtain the G mu hat, sigma hat, which is your point estimator. Okay, and this part is easy because you already know the MLE already, right? So that you can just put it in, okay, and then you can get your estimate. Okay, so which is equal to 123.0172. Okay, now then the next step is, so to construct the common interval, then the first step is you need to get the distribution of your estimator. Okay, then again, because this mu hat and the sigma hat is the MLE, and the sample size is sufficiently large. Okay, so according to what we know in theorem 2, so this estimator, okay, will has normal distribution with the mean equal to the true value. Okay, and the variance will be equal to this, right? Okay, so I just copy it from the theorem. Okay, and here, okay, so here the middle one is just what your covariance matrix of your MLE. Okay, and then this one is your A, this one is your A. Okay, so that's why you have that. Okay, now and then the next thing will be, so in order to get your converted interval, so then you try to calculate this variance. Okay, now then here so to calculate this variance, so you just follow the formula that what you have here. Okay, now so first of all, for the middle one, the covariance matrix, so we already know that this one is 0.1195 and then 0.059700. Okay, and then it remains to obtain this two vector, okay, which is your partial derivative of G with respect to mu and sigma. Okay, and then here, given that, so your function G is equal to the mean, right? So which is exponential to the power mu plus sigma square over 2. Okay, then here you can just differentiate it with respect to the mu and the sigma, then you get these two partial derivative easily. Okay, then once you have that, okay, then you can just put that in, and then you can calculate the variance. And then here, remember to construct the converted interval, so we will try to do the approximation on this variance, right? By replacing all the mu by the replacing all the unknown parameter by the MLE. Okay, so that here I will try to replace all the mu and the sigma by the MLE. Okay, and then here you try to do the calculation, then you will get the approximate value of this variance. Okay, now then once you have this, okay, then now you can start to construct your confidence interval. Okay, now and then here knowing that, so your G follow this normal distribution. Okay, so that means your standard score okay, which is the variance of G. Okay, so we'll have what the standard normal. Okay, and then you try to get your ZL and ZU. Okay, and then make this one to be equal to 95%. Okay, and of course here your variance can be replaced by this approximate value. Okay, now and then here to find this ZL and ZU, so again you are seeking for the symmetric confidence interval. Okay, 95% in the middle, 2.5% on the left, 2.5% on the right. Okay, now And then here, using the normal distribution table, then I guess it is not hard to obtain these two critical values. And then given this, then you can substitute ZL, you can substitute ZU, and then MLE, you got that, variance, you got that, then you will get the inequality for this function G. Then you just solve for this, okay, then you will get that, okay, the G will be somewhere between 17.69147 and 228.342, okay, and that will be what the 95% confidence interval. Okay, so here this is just another example on how do you find your confidence interval for your function of parameter when you have multiple parameter. So personally, I would say so the procedure is essentially identical to what we did for the single parameter case. Okay, just I would say the only difference is so because you have multiple parameter, so the variance of this estimate will be something more complicated, and you have to do that patiently. Okay, and of course in this example, so I have done a couple of simplification, like I give you the MLE and I give you the covariance matrix as well. Okay, of course in practice, if you in practice, so this is something that you also need to find. Okay, so of course so let's say for MLE, so I guess everyone know how to play with that, but just the tricky part is so to find the covariance matrix, so you need to get it by considering the inverse of this matrix I theta. So remember, I theta is equal to something very, very terrible. Okay, so like in these cases, so that means you need to calculate this stuff. Okay, bro. Okay, something like that. Okay, then you can calculate this expected value. Okay, something that we done that in the earlier example, and then you get your I theta, and then you take the inverse and get your covariance matrix. Okay. So basically here, we introduce a procedure on how do you find the confidence interval for your functional parameter. So which is useful for you to study various aspects in your loss model, like getting the probability, getting the expected loss, getting the expected value of total aggregate loss of stuff like that. Okay, so actually this delta method will be very useful for you to do this prediction. Okay, so I guess then that will be the end of this first online lecture. And the next time, so we will try to look at another aspect of the parameter estimation, which is very interesting one for me, is what we call the Bayesian analysis. Okay, so we will do that in the next online lecture. So that's all for today, and have a nice day.